Our next topic is mathematical induction. This is one of the nicest proof techniques there is in mathematics. It is extremely powerful and versatile. So we have been introducing the notation to be able to actually prove things using induction, and we will see how that works now. You can think of induction as a bunch of dominoes. You know those videos where a bunch of dominoes are standing in a line, and then the first one gets tipped, which causes a sort of chain effect of all of them falling down, and in the end, they all together create some sort of a nice picture. Mathematical induction is the mathematical version of the exact same process. So the idea in the picture here is we would like to go from all the dominoes standing up to all the dominoes lying down. And there's two conditions that must actually be true in order for us to be able to go from the beginning to the end. First of all, the dominoes all have to be spaced enough apart, but too close enough so that there isn't a gap too big so that the beginning dominoes fall down, but the rest of them are left standing. So it must be true that for any two dominoes, if the first one falls, the next one will fall as well. So that's one. And the second one is this exact same condition must be true for the first one. We should be able to tip the first domino in order to actually have the rest of them fall down. If this first domino is somehow against a wall or something like that, and we are not able to tip it, then the chain reaction will never be able to actually take place. So mathematically, let's quantify what those conditions might be. We're going to start by saying that we have some kind of statement, P of n, and it will depend on this value n for some integer n greater or equal than 1. So all of the induction proofs will essentially work for dominoes that are at least 1. Now, sometimes you will have a different starting value, and that's also going to be important. So the principle of mathematical induction, or sometimes that's denoted as PMI for short, is as following. First of all, as in this picture here, it must be the case that our first domino can actually be falling. So P of some value is true for some and not. Okay, so you have a value for which you can actually fall a domino. And secondly, it must be the case that if PK is true, so if I can fall this domino, then the next domino will also fall. So if PK is true for some K that is at least as big as this first domino's value here, then PK plus 1 is also true. If we can prove both of these assertions, then we have proven that P of n is true for all n that are greater or equal than our original small value. So if this is the case, then P of n is true for all n greater or equal than n naught. This first step we're going to call a basis step, and the second step is going to be called inductive step. Now, it's very important to realize that they are both essential in order for the proof to work. If the first domino cannot be fallen down, then none of the rest of them will fall. And if it's not the case that the fall of one domino will result in the fall of the next one, then of course, again, all of them will not be fallen. So both of these cases are extremely important for the induction to work. Now let's see how that's going to work with an example. I'm not actually going to prove anything in this example. I'm just going to show you how to set the induction up. So the statement is, for all integers greater or equal than 4, n can be written as a sum of 2's and 5's. So notice that here I have n greater or equal than 4, whereas in my original statement I had n greater or equal than 1. It doesn't matter as long as you actually have a starting value. It can be anything. A lot of the times it's 1, but sometimes it's not. So first of all, we can identify what is this statement that we would like to be proving things about. And of course, you can notice that the part of the statement that is not quantified, so this is for all integers, that's a quantifier, but the part of the statement, the predicate, is actually here. the fact that n can be written as a sum of 2s and 5s. That means that what I'm trying to actually prove is that for all integers, n greater or equal than 4, I have that property p of n holds. Next up is a basis step. Basis step determines the first value where this property will actually hold. So I need to show that p of some value, let's call it n naught, like in the previous notation, is true. Most of the time, you're going to take the smallest value that you're allowed to take and plug that in to see if it works. If it does, we're done. And if it doesn't, we pick the one higher and so on and so forth until you either persuade yourself that it's just not going to work or you find one where it does. So for example, in this case, we can test it out with 4. Is it true that 4 can be written down as a sum of 2s and 5s? Well, 4 is 2 plus 2, so it certainly can be written down as a sum of 2s. So for our basis case in this particular example here, n naught will be 4. I'm going to leave it in the general form, but keeping in mind that this will always be a particular number. Next up is, I would like to actually separate inductive hypothesis. So let's take a look at the inductive step here. You notice that this is a conditional if-then. Digging in your memory about the first unit in this course we've covered, remember that a conditional has a hypothesis, which is the first part, and a conclusion, which is the second part, which means that the inductive step actually consists of hypothesizing or assuming the first part of the statement and proving the second part of it. Because sometimes these statements are sort of complicated, I'm actually going to write them each out separately every time. So my hypothesis is this first part of the conditional. So for inductive hypothesis, I'm going to assume that P of K is true for some K that's greater or equal than n naught. Again, because I've actually already checked 4, I know that this is going to be true for K greater or equal than 4. But because I would like to keep it in generality, I'm going to keep it this way, okay? The inductive step will consist of actually proving the second part of this statement. So now I'm going to prove that P, K plus 1, is also true. Once I've done that, by the principle of mathematical induction, I'm actually done. By the principle of mathematical induction, I've shown that the first domino can fall and that every other domino will cause the successive one to fall as well, which means that all the dominoes will be laying flat. So once I've completed this proof, I'm actually going to be done. So let's assume I actually have that and see another way to persuade ourselves that this will result in proving that the statement is true for all integers and greater or equal than some fixed value. What we actually have is, again, you can think of that in terms of dominoes, or you can think of that as a chain of implications. We are going to start with the smallest one that we have shown using the basis step is true. So you begin with saying P of n naught is true because this was checked in your basis step. Then the inductive step tells you that you're assuming P of K is true for some K greater or equal than that. So in particular, this is true. And you've just proven that that means the next one is true as well. So next up, we're going to have that P of n naught plus 1 is true. And this is by the inductive hypothesis. I'm going to label it as IH, inductive hypothesis. Right? The inductive hypothesis says specifically that. Assume that one step is true, and we have proven that the next one is true. Now, if the next one is true, we can now take that to be our inductive hypothesis, and by the inductive step, we've proven that the next one is true. So the next one is implied by the inductive hypothesis as well. So P of n naught plus 2 is true. And of course, I can carry on this way forever and ever, right? I don't have to stop at any particular point. What I'm doing is I am at each and every single time can use this proof that given a certain step, I have the next one, and this chain of implications can go on forever, just like the dominoes. Okay? That's the general setup. Let's see how this works with a particular formula. We're going to, in fact, prove several of the formulas we've already seen. We're going to start off with proving the formula for the sum of the first n integers. So we've seen that proof sort of by combining the integers from the beginning and the end. We're now going to use induction to show that it's true as well. So my property is this. So my p sub n is this guy right here for all values of n greater or equal than 1. In the basis step, I'm going to find the small value for which it's true. And again, you always start with the smallest one possible to see if it works. So I'm going to see, is it the case that property as when n equals 1 actually holds? So when n equals 1, what do I have here? I'm going to sum numbers from 1 up until 1. So on the left-hand side, I have 1. And according to the formula, what I should get is this expression here. So let's plug in n equals 1 and see what happens on the right-hand side. Whoops, it's going to be 1 times 1 plus 1 over 2. So my question is this actually equal? If it's equal, then the property for 1 holds. And if it's not equal, then the property for 1 doesn't hold. And I'm going to try maybe with a 2. So is this true? 1 times 2, so this is going to be 2 divided by 2. 2's will cancel out, and I'm going to have 1 is equal to 1. So yes, this in fact holds, which means that p of 1 is true. I have checked my basis step. As I said, the basis step is usually the easy part because you're actually checking the property with a specific number. So now I can move on to my inductive hypothesis, what it is that I need to prove, and then the actual proof. Notice that I'm going to write it out explicitly what I'm after so I can keep my eyes on the ball for where I need to go with my proof. So the inductive hypothesis, remember, this is the first, let me scroll up here. This is the first part of the statement here. P sub k of k is true for some k greater or equal than my n naught, which in this case is 1. So my inductive hypothesis is suppose or assume pk is true for some k greater or equal than n naught. And n naught is the value that you've checked in your basis case. So in our case, it's 1. Now, this is not terribly insightful because it's too general, but I have a particular example here. So I'm going to actually write out what that means in this specific case. So if I'm supposing p of k is true, that means that I'm supposing that this formula holds for k. So 1 plus 2 plus 3 all the way up to k is in fact going to be equal to k plus 1 over 2. Good stuff. What do I need to prove? What I need to prove, again, according to the principle of mathematical induction, is the fact that pk plus 1 is also true. So again, let me write it out here in generality. I'm supposed to prove that p sub k is 1 is also true. But again, because I actually have a particular case here, I can write it out using specific things that I need to prove. So I need to prove pk plus 1 is true, which means this statement, but with n being replaced by k plus 1. K plus 1, k plus 1, k plus 1. We're going to have to be very careful plugging in k plus 1 everywhere that we see n, so that we're actually doing this properly, right? So 1 plus 2 plus all the way up to k plus 1 equals, and then I'm going to see what I have on the right-hand side here. So again, I'm substituting k plus 1 for n. So I'm going to have k plus 1, and then it's k plus 1 plus 1, so k plus 2 divided by 2. So I am going to assume that this is true, and I have to show that this is also true. In the inductive step, that's where the proving actually occurs. So I'm trying to prove this is the case. So I'm going to start with the left-hand side, do some manipulations, and hope to arrive to the right-hand side. So let's take a look at the left-hand side here. So I have 1 plus 2 plus 3 all the way up to k plus 1. Now, the one thing that you are going to notice being used in inductive proofs over and over again, I have this thing to use. So this is something I really hope to employ somewhere in the middle of my proof. So in the need to prove, always think about what happens right before here. I was counting from 1 all the way up to k plus 1. before k plus 1, my previous term, of course, is just k. So here, I should remind myself of that, and let me include this here too. So I have 1 all the way plus k, and then I have the next term, which is k plus 1. Why is that useful? Because look, this expression right here from 1 to k is exactly the one that I've supposed in the inductive hypothesis to actually have the property pk. So this is where I can apply my inductive hypothesis to. This already has a formula because I've supposed that that's going to be true. So I can sub that in for the formula. So 1 plus 2 plus all the way up to k is k plus 1 over 2 as per the inductive hypothesis, right? So I've just subbed that in for 1 plus all the way up to k. And then, of course, I have this my leftover k plus 1. Okay, I'm going to try to put this stuff together. Remember, this is the expression I would like to see on the right-hand side, so I'm going to see if this is actually going to result in that. So what do I do here? Well, this has a denominator of 2, this one doesn't, so I'm going to introduce the denominator of 2 here. I'm going to multiply it by 2 and divide it by 2. So altogether then, I have k plus 1 over 2 plus 2k plus 1 over 2, right? I literally just multiplied and divided it by 2 right here. Now that they have the same denominator, I can put them together. So what I'm going to have is k plus 1 plus 2k plus 1 all over 2. Excellent news. Now, is there anything else I can do to simplify this expression right here? Well, I notice, of course, I can open up the brackets, but I also notice that this bracket is actually the same. So I can, in fact, factor it out from both of these terms. So I will factor out k plus 1, and what I'm going to have left is k plus 2. So I factor out k plus 1, and I have k plus 2 left in the brackets. And this is very exciting news, because this is exactly the expression that I was hoping to prove that it actually equal to, and therefore I am done. So in conclusion, by principle of mathematical induction, P of n holds true for all n starting with my base case, which in this case was 1. This is how induction is always going to work. We're going to go through several more examples, but let's take a pause here for a second to go through the structure. Induction is a very structural proof. You literally have to lay out steps very carefully and then proceed to actually show that what you wanted to show. So we're going to start off with the basis step. We're going to check the property for some small value. If it's true, basis step is true, and we carry on. In the inductive hypothesis, we will assume that the property is true for some value k, greater or equal than that in the basis step. And again, given a specific example, take time to write out what that actually means. We are going to need to prove that the next step is also true. And again, it's better to explicitly write out what that means. In the inductive step, we're actually going to carry through with the proof of what we wanted to show. And if it does work out to be the same, then by the principle of math induction, we have completed the proof. Let's see how the structure is going to work in other examples as well. Next up, we have the example that says to prove that for all integers n greater or equal than 1, we have 2 plus 4 plus 6 plus 8 and so on all the way up is equal to n squared plus n. So instead of like the previous example where we have the sum of all the numbers from 1 to n, here we have the sum of all the even numbers from 2 to 2 to the n. And this has also a formula that we will be able to use. Let's see. Basis step is proving that the property holds for the first value. So before we proceed, it's actually better to label what the property is. This is my property Pn. Basis step, again, I'm going to take the first value that I am given and hope that it actually is true. I'm going to check whether this holds for n equals 1. If my n is 1 right here, 2 times 1 is just 2, so my entire sum is no more than just one term. So on the left-hand side, I have 2. What do I have on the right-hand side? On the right-hand side, I have 1 squared plus 1. And the question is that property or is this equation actually satisfied? Well, 1 squared is just 1, 1 plus 1 is 2. So yes, in fact it is, which means that P of 1 is true and our base case is completed. Inductive hypothesis is going to be assuming, since this is our first example, or second example only, I'm going to actually write this out fully in generality and then in the context. So I'm going to assume that PK is true, which means that 2 plus 4 plus 6 plus all the way up to 2k is actually equal to k squared plus k for k greater or equal than the base case, which is 1. I'm going to need to prove that P of k plus 1 is true. P of k plus 1 is true. And what does that mean in this case? In this case, that means 2 plus 4 plus 6 all the way up to the kth term, which is 2k, plus the next term, which we're submitting k plus 1 in for n, is going to be 2 times k plus 1. So you got to be really careful here. This is not 2k plus 1. I need to sub in k plus 1 in where I see n. So I need to multiply 2 by the entirety of k plus 1. Okay? So this also is what actually keeps this term even as opposed to odd. And on the right-hand side, replacing n with k plus 1, I'm going to have k plus 1 squared plus k plus 1. So this is what I am trying to prove here. Okay? And that is where my inductive step will actually, it will be going through the proof. So I'm going to start with the left-hand side, and I'm just going to copy it over. And what I'm trying to show is that the left-hand side here is actually equal to the right-hand side by various ways to actually simplify or apply inductive hypothesis to it. So again, I'm going to see the P sub k case as part of my pk plus 1 case, right? So this is right here. Therefore, I can replace it with my assumption that this equals to k squared plus k. So let's highlight this. And by the inductive hypothesis, this is actually equal to k squared plus k. Okay, so I can write equals here, and I do have to justify why that's true. That's true by inductive hypothesis. I'm not just taking it out of from some random space over here. This is now k squared plus k, and I have my last k plus first term still to be added, 2k plus 1. Now, there's a number of ways to actually simplify this expression, and this is why it's important to write down what it is that you need to prove. What I want to see is this, not just any random simplification of this value right here. I would like to show that this is actually going to simplify to that. So I'm going to try to manipulate it so it can actually look like that. So let's see. Let's open up the brackets here maybe. So I'm going to have k squared plus k, and then I have 2k plus 2. If I rearrange this a little bit, again, keeping in mind what it is that I want to see this k plus 1 squared term. So maybe in your rough work on the side, you can think about what that represents. K squared plus 1 is k squared plus 2k plus 1. Remember from the binomial theorem a few lectures ago? So I would like to actually have this all together. And I can see that I have k squared, I have 2k, and I have a 2 here. Now this 2, I can actually rewrite a little bit more conveniently as 1 plus 1. Some major simplifications here. Now, look here. I have k squared, I have 2k, and I have 1, which all together forms k plus 1 squared. Because addition is commutative and I can move stuff around, I can see all of these terms together. So k squared plus 2k plus 1 at first. And what do I have left over that I haven't highlighted? I have the k and the 1. So k plus 1. So now I know that this, what's in the brackets, will give me k plus 1 squared. And what I have left over is k plus 1. And that is exactly the expression that I needed to actually prove. So we're done. Again, in conclusion, by the principle of mathematical induction, P of n is true for all n starting from our base case. So here, greater or equal than 1. Fantastic. Okay, so again, reviewing the steps, take the basis step as some small number, write out what your inductive hypothesis as an assumption is, write out exactly what you need to prove, and then go ahead through with the proof. Next up, we're going to prove the formula for the finite geometric series using induction. So we've proven it using algebraic manipulations. Now let's see how it will work using induction. So once again, first things first, I'm going to label this property as P of n. For the basis step, we're told that n can be greater or equal than 0. So I'm going to try 0 first, because that's the one that is there. So let's see what happens if I plug in n equals 0. Now notice that my r here is a constant. That is my multiple that forms the geometric series. So what I'm inducting on isn't r, it's the power, the n. So if the power is 0, then I have r to power 0, which is just 1. So the number of terms in this sequence is just 1, just the first one. And on the right-hand side, what happens if n is 0? Let's just plug it in. So I have 1 minus r to power 0 plus 1, so 1 divided by 1 minus r. Is that equation true? Is this actually correct? Well, 1 minus r and 1 minus r will cancel, so that will be a 1 on the right-hand side, and it's a 1 on the left-hand side. So indeed, it is true, and therefore p of 0 is true. And our base case is satisfied. Fantastic. Next up is inductive hypothesis. So next up, I'm going to assume, let me write that down, assume P of k is true for some k greater or equal than the basis case, which is 0. So what that means I'm assuming is that this expression is true when n is equal to k. So 1 plus r squared all the way up to kth power is in fact, does actually satisfy that formula. So 1 minus r to the power of k plus 1, 1 minus r. Fantastic. Next up, what it is that I need to prove. I need to prove that p of k plus 1 is also true, which means I have to plug k plus 1 into here and then write out what that means. And again, remember, because we will almost certainly, well, we better be actually using the inductive hypothesis if we're using induction, it's better to write out the k terms first. And then remember that altogether, I need k plus 1 of them. So all the way up to k, and then the next one is going to be k plus first term. And what I'm trying to prove is that this property holds when n is equal to k plus 1. So once again, we're going to be very careful replacing this n with k plus 1. So what I have is 1 minus r. Now, if this is replaced with k plus 1, I'm going to have k plus 1 plus 1. So altogether, we're going to have k plus 2 divided by 1 minus r. This is the expression or the equation that I'm trying to prove. Okay. In the inductive step, I'm going to start with the left-hand side. So let's take the left-hand side, copy it over here. And as before, this is going to be exactly the same way in all of the inductive proofs. In some cases, you have to work a little bit harder at it first. With summations, it's actually very straightforward. So what I have here is this portion is exactly the one in the inductive hypothesis, so I can replace it directly with what I assumed is true. So here, by inductive hypothesis, I can apply that this will be 1 minus r to power k plus 1, 1 minus r equals, and again, I actually have to, at this point, justify saying that this is by inductive hypothesis. I need to give a reason for why I can write this down as equality. So now I'm replacing that first chunk of my entire summation by this new expression. 1 minus r to the power of k plus 1, 1 minus r, plus that last k plus first term that I've added. And just as before, now I know that I need to somehow massage this expression in the hopes to see this at the end. So notice that here I only have one denominator, whereas here I have two separate chunks, which means that I should be doing common denominators on these two terms. So I'm going to take this term, multiply it by y minus r, and divide by 1 minus r. So my first fraction is going to stay the same, but for the next one, I'm going to have what I have, r to the power of k plus 1. I'm going to multiply it by 1 minus r, and I'm going to divide by 1 minus r. Now that everything is on the same denominator, I can bring the two fractions together. Okay, I'm not going to skip steps here, so I'm just going to rewrite it. 1 minus r. Excellent. And next step, I'm actually just going to open up these brackets. So what I have is 1 minus r to the power of k plus 1 plus, let's see, r to the power of k plus 1 times 1 is just r to the power of k plus 1. And next up, I have r to the power of k plus 1 times negative r. So first of all, I'm going to have a negative. And then what happens to the powers when you multiply two things together is you add the powers. So this has power of 1. So my new power of r will be k plus 1 or k plus 2 all over 1 minus r. Now I stare at this expression and I notice that these two terms are the same, so they will very nicely cancel each other out. And what I will have remaining is 1 minus r to the power of k plus 2 divided by 1 minus r, which happily is exactly the expression that I was hoping it was going to equal, so I'm done. By the principle of mathematical induction, we've just proven that this property holds for all n starting with the base case, which in this example was 0. Excellent. Yet another example of induction being applied successfully. Now, I have two more examples on this page here, but the first one is extremely similar to the ones that we've already been working with because it's also dealing with powers. So I strongly encourage you to pause the video right now and actually try it for yourself. You can watch me do induction all day, but it's not going to make you better at it until you do 5 or 10 exercises yourself. Go ahead, pause the video, and then come back. Okay, so my property here is, of course, this one, and my basis case is going to be 0. So if I plug in 0 into the n, what I have to check now is if n is 0, I have 2 to the power 0, which is 1. So using only one term on the left-hand side, is the property going to hold? If n is 0, I have 2 to the power 1. Let me write it down. 2 to the power 1 minus 1. So is this equality true? Well, 2 minus 1 is 1, so it's in fact equal to 1, which means that p of 0 is true, and that forms our base case. This proves that that first domino can in fact be fallen. The inductive hypothesis, I'm going to assume that p of k is true for some k greater or equal than 0, or I can just write down the expression directly, except for, let me say, assume. So what I have is 1 plus 2 squared all the way up to 2 to the power k is equal to 2 to the power k plus 1 minus 1 for some k greater or equal than the basis case, which is 0. I need to prove the exact same expression, but now for k plus 1. And again, it's better to write out what it is that we have up till k, and then include the k plus first term. And replacing n with k plus 1, what I have here is k plus 1 plus 1. So the expression on the right-hand side will turn into k plus 2 in the power minus 1. The inductive step will hopefully actually prove this assertion. So let's copy it over, paste it out here. What I'm going to have, again, I have just written out the first k terms, so they're obvious, and therefore I can see that by inductive hypothesis, this is exactly the expression I have, which means I've assumed it's equal to 2 to the power k plus 1 minus 1. So equals, and again, I have to justify this equality by saying that it's true by inductive hypothesis. So I have 2 to the power k plus 1 minus 1 plus, and then I have my k plus first term remaining, 2 to the power k plus 1 over here. Again, the reason to write out what it is that you need to prove is so you can keep your eye on where you're trying to get to, okay? So what I have is 2 to the power of k plus 1 plus 2 to the power of k plus 1, okay? I have an apple plus another apple, which makes for 2 apples. So what I have here altogether is 2 of the 2k plus 1s, and then don't forget your minus 1 over here. Now, this 2 has a power of 1, and this 2 has a power of k plus 1. When I multiply, I add the powers together. So 1 plus k plus 1 is equal to k plus 2 minus 1. And I have arrived at the exact same expression as the one that I was trying to prove. So we are, in fact, done. By the principle of mathematical induction, P of n is true for all n above the basis case, which in this case was 0. Okay? Hopefully, by now you're getting the hang of it. It seems very mechanical, and that is because the properties we're trying to prove are very algebraic. We will see induction being used in other ways soon, and then later on in the course, which will make it very clear that it is much more flexible of a technique. For now, we're just trying to do kind of like the drills with the induction, so we are comfortable with simply performing the steps. Next example, last one on this page, we're going to deal with the summations and the factorials. So again, this is going to be very similar to the questions we've seen before, except for now this is actually using the summation notation, which you can expand out. So I encourage you to pause the video and then come back to go through the question together. Try it, see if you can get through it, or you will find out where you are stuck and therefore will find out your weaker point that you need to practice more. Okay, so here is our property P of n. And as I said, you can leave it as a sum or you can write this out. So maybe let's write it out so it's easier to see what the summation on the left-hand side actually is. So this is the same as going from index 1 up to n of I times I factorial. So 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial all the way up to n times n factorial. And the alleged simplification is the fact that this whole thing is equal to n plus 1 factorial minus 1. All right, so what do we have here for the base case? The base case, we're saying that we're trying to prove that it's true for all n greater or equal than 1. So let's see, I have n is equal to 1. What do I have on the left-hand side of my expression here? Then I will go from 1 to 1, which is actually why the summation notation for this is a little bit better. So I'm only going to have the first term here, 1 times 1 factorial. And the question is it true that it's equal to the right-hand side of this expression when n is equal to 1? So 1 plus 1 factorial is going to be 2 factorial minus 1. Let's see, this is simple arithmetic. 2 factorial is 2 times 1, so 2. 2 minus 1 is 1, which is of course equal to the right-hand side being 1 here. So P of 1 is true in this case. Excellent. For the inductive hypothesis, we are going to assume that our statement is true for some k greater or equal than the base case, which is 1. So I'm going to assume that 1 times 1 factorial plus 2 times 2 factorial all the way up to k factorial is in fact equal to this expression when n is replaced with k. And this is going to hold true for some k greater or equal than the base case, which is 1. We're going to need to prove this exact same expression, but when n is equal to k plus 1. So we're going up one more step into the sum. So we want to prove 1 plus 1 factorial, 2 times 2 factorial, all the way up to k times k factorial, plus the next term, which is k plus 1 times k plus 1 factorial, following the pattern, is equal to, and again, you got to be careful, because in the need to prove, we're replacing n with k plus 1. So we're going to have k plus 1 here. K plus 1 is equal to k plus 2 factorial, and then we have that minus 1. Okay, and in an inductive step, we're actually going to go ahead and prove that this is the case. So I have this expression here. Not surprisingly, once again, I see that the part of it is, in fact, the induction hypothesis itself. This expression is a part of the inductive hypothesis, which means I can replace it with the thing that I've supposed it to be true. So k plus 1 factorial minus 1 equals, and again, I need to include my justification for this equality. And what I have is k plus 1 factorial minus 1. Now the rest of it I have to rewrite. So I have plus k plus 1 factorial. Lovely. Okay, this is allowing me to see where it is that I'm supposed to get to. So let's keep the eye on the ball here. I have to have one single factorial and then a minus 1. So the minus 1 I sort of already have, but the k plus 2 factorial I'm still working on. But I do notice that this term has k plus 1 factorial and this term has k plus 1 factorial. So I can factor out the k plus 1 factorial out of the both of them. This is where practicing simplifications with factorials early on will come in really handy. So I'm going to take out k plus 1 factorial from those two terms. What do I have left? If I factor out k plus 1 factorial out of the k plus 1 factorial, it's kind of like, let's say if I had a 5 here and I factor out a 5, what I have left is 1. So this is going to be left with just 1. But taking this, if I factor out k plus 1 factorial, what I have left is k plus 1. So plus k plus 1. And I better not forget this negative 1 on the outside that I haven't actually done anything with. Okay, so what do we have? K plus 1 factorial. And of course, what I have in this bracket is k plus 1, so k plus 2 minus 1. Now, remember that factorials are kind of collapsing. So k plus 1 factorial is 1 times 2 times 3 all the way up to k and then k plus 1. And now I'm multiplying this thing by k plus 2. So all together, I actually have k plus 2 factorial. Factorials have this really nice extendable multiplication property that makes them easy to work with if you're going to multiply the two of them together. So this entire expression in the front here is actually equal to k plus 2 factorial. And then, of course, I better not forget my minus 1 that I had there. And this is great news because this is exactly the expression that I was hoping to prove. And we have, in fact, proved it by applying the inductive hypothesis and then by simplifying through the expressions. So overall, by the principle of mathematical induction, my property P sub n is true for all n above the base case, which in this case is 1. And there we go. We will see more examples in the next lecture, but these are some of the basic ones to show the structure of inductive proofs. So make sure that you're comfortable with all the steps in the middle.